Hi friends, in this video, let's learn how to design a solution for a machine learning problem. So these are often referred to as machine learning solution design problems. Again, these are some problems that you might encounter, especially for senior roles in machine learning or for software engineers with experience who are interviewing for machine learning roles. So again, apart from interviews, this is a very interesting problem to solve, to understand how to design actually a solution. This is not exactly about picking one algorithm versus the other. It's about, given a real world problem, what are the building blocks that you'll use to design an end-to-end solution, right? So let's start very first. Let's understand the problem. This is a problem about searching question and answer repositories. So imagine companies like Stack Overflow, right? Stack Overflow sits on millions of questions that people ask questions for, and there are answers available for them. So imagine if you were a machine learning engineer or a machine learning scientist at Stack Overflow, how do you design the Q&A search? Or this could also be at Quora. Again, these are some of the popular websites that we all encounter. But this problem of searching question and answer repositories not only exists in these internet companies, they exist everywhere. For example, imagine a company which has a customer service portal, right? In the customer service portal, people can ask questions. The customer service representatives respond back with answers. That is a huge treasure trove of data with question answer pairs. Similarly, companies might create FAQs, and these customer service portals could be there for any company. It could be a mobile phone service company. It could be any company for that matter, right? So lots of companies, both big and small, sit on a large repository of question and answers, which are typically either in the form of FAQs or they are in the form of interactions with the customer service personnel. They could even be in emails, right? A customer might send an official email to the official email address saying, hey, I am encountering this problem. Can you help me with it? Or this could be discussion forums like what you have in Stack Overflow and Quora. This could sometimes be also in the form of audio and video, right? It could be in a form of a video discussion with a customer, or this could be some videos that your team has made to respond to customers' questions. It could be in the form of audio, phone calls, whatever it is. So most companies, both big and small, are sitting on a gold mine of question and answer data. And now, how can we search this whole database very efficiently at a very high speed? So it's not very uncommon to imagine data sets with hundreds of thousands of questions and answers, either in the form of emails, discussion forums, customer service portal requests, FAQs, etc. Let me give you an example. Imagine on Stack Overflow or any such platform, right? So if there is a question on how to insert, I'm an end user. I don't know how to install a tool called pip. Pip is actually a very popular tool in Python. So imagine if I ask this question, which is how to install pip. One way to do it is, can you find questions which are very similar to this in this huge repository of hundreds of thousands of questions? Can you build a system S which can pick the most relevant questions in our huge database of questions and answers? Can we pick the most relevant questions and show it to this user so that this user, and we need to do it very, very fast. So can we do it fast enough so that this user, if such a question, if a question very similar to this exists in our whole data set, can we pull it and give it to the user so that the user's question is answered immediately? Imagine if such a question does not exist, then you can say, okay, sorry, we don't have a question very similar to this. We'll post it to our customer service portal, or we'll post it for others to answer. But if something very similar to this already exists, it makes much more sense to respond back with the answer immediately to the user, right? So if you think about it, what are the objectives of the solution? Again, whenever you're doing a machine learning solution design, you should always ask, what are the objectives? Obviously, one of our key objectives is a faster response time to the user. From the time a user asks a question, we want to be able to do it in just under a second, maybe. Very quickly we want to do it, right? So that's very important. And given the size of companies, we might get thousands of user queries every few minutes, right? So we also want this to be scalable if you think about it. Again, scalability is a property of the size of the company. Some companies like Quora, Stack Overflow, or large companies with huge customer service like Amazon, they might get hundreds of user queries per second. And again, this will lower our service costs, because if there is a question that is very similar to this that is already answered, which is available in our repository of questions, then we don't have to keep sending this to our customer service personnel. So the business objective is also to lower the service costs, the customer service costs. And also it enables better utilization of all the knowledge that we have in-house. Right? These are the three broad objectives from a business standpoint and also from an engineering standpoint. Now let's look at it, right? So a typical software engineer, right? The software engineering approach to this is as follows. Imagine that this is the repository of all the data that I have. The typical software engineering approach to this is, let's do a keyword-based text search, right? So a keyword-based text search basically looks like this, okay? Imagine if this is my question. I want to index this question in such a way that I want to find all the documents that contain this word. Again, here, let's define a document as a pair of question and answer. So given a question, it could have one answer or multiple answers, depending on the context. But a question along with all the answers, let's call it a document, just for simplicity, right? Now, every document which contains the word how, right? We want to first fetch them very quickly. Similarly, every document which contains the word to, let's assume D1, D3, D5, D7, D9 are the documents which contain the word to. Similarly, all the words that contain install, all the documents that contain the word pip, right? Now, amongst all these documents, we want to find the common document. So if you notice, D3 is here, D3 is here, D3 is here, D3 is also here, right? This is the simplest form of keyword text search. Okay. So what are we doing? We are breaking a given sentence into words and we are searching for documents, which is nothing but question answer pairs, which contain these words, and we are trying to find an intersection of all of them. So here we can say D3 contains all these 4 words, and hence D3 might be a potential similar question to the question that the user is asking, right? This is how typical keyword text search works. Again, those of you who are software engineers who know some data structures and algorithms might know that keyword-based text search can be built using a concept of inverted indices. So there is a concept called as inverted index in databases, also in typical data structures and algorithms, which is very popularly used. Again, you need not implement an inverted index logic from scratch. Oftentimes you have open source technology, like for example, you have Elasticsearch, which is a very, very popular distributed keyword-based text search platform, right? It is extremely scalable. It is extremely fast. You can answer thousands of queries per second. It's extremely scalable. It has all the inverted index is a very basic data structure, or at least one of the data structures that is used in Elasticsearch. But an engineering approach to this is, let's take all this data, convert them into keywords. Then we'll use the concept of inverted indices. And instead of implementing our own inverted index based system, let's use Elasticsearch. Again, I will not be able to go into the mathematical details or the algorithmic details of inverted index because I'm giving a high level overview here. Because this is a design solution, right? This is not, again, when you go into low level design, when you write code, you'll have to know more details. But I'm giving you a big picture view here. So what a software engineer might say is, okay, this is all cool. All this is cool. So what we'll do is simply, we will convert all of this into question answer pairs. Again, you'll have to give more details into how will you write each question. Again, I'm assuming that if you don't know how Elasticsearch works, it's very simple to learn, right? It's a very simple tool to learn, and you can ingest or index all of these documents. And whenever somebody asks a question like this, you can quickly find the documents which contain these words. And of course, Elasticsearch also gives you simple schemes to rank these documents based on how relevant they are in the context of how often these words occur and things like that. Of course, you can improvise the solution by saying, okay, I will ignore stop words like to, right? Instead of using just 1 grams, you can use n grams, which is very common technique that is used in text search. Similarly, instead of indexing both questions and answers, you can say, I'll only index questions. These are all design choices that you have at your disposal. But here comes the interesting part. What if we want to do semantic search? For example, let's take these two questions. The first question is how to install new packages in Python. The second question is use new library via pip3. Now, if you notice, there aren't many common words here. There is a common word which is new here, right? But there aren't many common words between these two questions. Imagine we already have an answer associated with this question in our repository. Imagine we already have that somewhere in one of the documents. Now, if a user asks this question, can you use some techniques in natural language processing? Can you use machine learning here to perform semantic search? Can you realize that this question and this question are very similar, even though they are worded differently? Now, here the problem is if you use a pure software engineering inverted index based approach, if you use a pure inverted index based approach, it may not work well. The reasoning being that there are very few common keywords here. Then you might say, okay, I'll use synonyms to words like libraries. There are some hacks around it. I'm not saying there are no software engineering solutions to this, right? I'll also say that, okay, Python and pip are synonyms or something like that. There are some software engineering based approaches also, but a much more elegant approach to solve this semantic search problem is using, think about it. If you were to think about a solution, what would you think about? If you were to solve this problem, we all know about text vectors. There are very popular text vectors like BERT, right? BERT is one of the most popular and most recent algorithms, wherein given a sentence, you can represent it using a dense vector. Right? This is one of the most popular algorithms right now. Again, there are tons of variations of BERT, but I'm just using BERT as a general technique itself or general class of techniques. Now, what if in addition to doing keyword-based search, if we can represent this whole question into a vector, let's assume we can represent this as a 512 dimensional vector. Let's just say, imagine we can also represent this whole thing into a 512 dimensional vector. Because BERT uses NLP techniques, this 512 dimensional vector and this 512 dimensional vector, these are dense vectors, would show that this question is fairly similar to this question. But imagine that we could have a large number of questions. So this is all about imagine if this is the question given to us, you will have, again, for this question, we can quickly compute the BERT vector for it. Now there are BERT vectors computed for each of the questions in our database or in a data repository. Now we have to perform a nearest neighbor search for this query question. For this vector, we have to find nearest neighbor search and do it fast, right? Now, that's an interesting challenge computationally, right? So one way you can design this solution, again, this is a very, very high level overview. I've not gone too deep into the details here, but imagine all the text data you have, you build a data corpus. This text data could be emails, it could be FAQs, it could be your portal, your customer service portal data. In this corpus, every document DI is represented as a pair of question and answer. Similarly, if you have audio and video data, you can apply standard speech to text techniques, either something that you have in-house or something that a cloud-based speech to text from Google or Amazon or Microsoft that you can use. And again, we have shown some examples of how to build this in some of our previous public live sessions. You can just convert your audio or video into text and inject that data also into your corpus. So your corpus contains both text data and speech to text converted audio and video data. Now this whole corpus of data, you will build an index, you will index this whole data using Elasticsearch, right? This is standard keyword based indexing. Now on this whole corpus of data, you can take each of the questions you have, compute the BERT sentence vectors for each of these questions, and inject or insert these vectors also into the Elasticsearch. As of mid-2019, there is a very nice announcement from the Elasticsearch team. I'll also provide you a link to that blog where Elasticsearch from version 7.3 onwards has an inbuilt facility to also have dense vector representations for text. Earlier, this was not available in Elasticsearch implicitly, so people had to write add-ons to Elasticsearch. Thankfully, from middle of 2019, we can, for every document or for every text snippet that we have, we can compute the BERT dense vector representation, and we can also add this dense vector representation for each of the questions into our Elasticsearch index. Now, Elasticsearch implicitly within the Elasticsearch code base, it does the nearest neighbor fairly well, reasonably well. Okay. So now what happens is when a user gives a question, let's assume the user gives a question, we will send this question. On this question first, we will compute the BERT vector. Look at this. We will tokenize this sentence. Okay. Again, Elasticsearch can do that for us. So just pass this question to Elasticsearch, perform keyword search on it. Also, compute the BERT vector representation that you have for this question, and Elasticsearch can help you compute cosine similarities with all the other questions that you have in your data repository based on BERT vectorizers. Now, using both keyword search and cosine similarity search, Elasticsearch can give you a list of top documents, which is basically a list of top question answer pairs that are most relevant given this question. Again, all of the magic is happening. Look at this. Internally, what Elasticsearch is doing is it is doing keyword based inverted index search or inverted index based keyword search. It's also doing a dense vector, like a sentence vector BERT based cosine similarity search. From Elasticsearch version 7.3, there is a nice announcement in the middle of 2019. Earlier, people who did it, including myself, we had to do it using ad hoc techniques, but now it's all inbuilt into Elasticsearch. So if you were to build a solution like this, it's very simple today, right? Earlier, it was slightly more complex because we had to implement our own nearest neighbor search. Now, Elasticsearch does that for us, thankfully, right? Now, what do you do? To this user, you say, okay, these are the top 3 questions. You can give top 3 questions and say, these are the top 3 questions that are very similar to your question from our repository. Do any of these questions answer the actual question that you asked? Okay, do the answers for any of these 3 questions are relevant in the context of the question that you asked? If they are, great. If they are not, they'll simply say, the user can say, no, they are not relevant. Please submit it to customer service, or please submit it for others to answer, right? So this is the high level overview of things. Now here comes another question, very important design question. What if we have billions of documents? Again, billions of documents is typically internet scale. Okay, companies like Google, even Facebook, Twitter, those are the companies that have these billions of documents, right? A typical customer service or emails may not have billions of documents, and Elasticsearch scales to even millions of documents reasonably well. But when it comes to billions of documents, again, I haven't tried the Elasticsearch cosine similarity on billions of documents because I don't have access to that data enough. But if you were to design this solution for billions of documents, it's certainly a good thing to first try Elasticsearch. If it works, great. But otherwise, there are specialized techniques, especially built at companies like Facebook and Microsoft, also some startups and universities that work very well here. For example, let me give you an overview here. There is a paper and a software, open source software, which was open sourced by Facebook, called as Facebook AI Similarity Search. It's called FAS. Okay, this is a paper that was published in 2017. I will provide a reference link to this paper a little later, right, in the description section of this video also. So here, Facebook actually used GPUs to build a nearest neighbor search on vector representations of images. Okay, this paper actually uses vector representations for images, but the same thing can be used for text. At the end of the day, what you are performing is a nearest neighbor based search when each of the documents or each of the images are represented using dense vectors. In the case of images, these might come from pre-trained convolutional neural network models, right? So the same technique, again, FAS can be used for text also. It's a GPU based solution, very, very efficient code. They've used this is code written in C++ using brilliant libraries like BLAS. They use a lot of simmed vectorization. They also use a lot of multi-threading. This is very, very efficiently written code. And it runs 8.5 times faster than previously known best GPU implementations. Okay, they also use some nice algorithmic advancements and ideas. But all in all, this is a technology from 2017. A much more recent innovation here is from Microsoft Research, and this paper is called as DISC-ANN, Approximate Nearest Neighbors. This paper is from the NIPS conference or Neuro IPS conference from late 2019. And in this paper, Microsoft Research scientists along with university collaborators have shown that if you use a solid state drive based system with about 64 GB of RAM, a solid state drive and 16 core, this is just one system. One system with this configuration can handle over 5,000 queries per second for nearest neighbor search, and it can respond in under 3 milliseconds. And they use some very innovative graph-based strategies for computing this. I'll also provide a link to the paper which explains DISC-ANN in more detail. So very often when you're trying to solve a real-world problem like searching Q&As in the real world, you start with techniques and technologies that we understand well. That should always be the first strategy. So that's why the first cut solution that I suggested is, okay, we know how Elasticsearch works. Inverted indices have been there for over 30 years now. Elasticsearch is very, very well built. We know about BERT. So let's use all the platforms that already exist. So Elasticsearch thankfully can do keyword search from version 7.3, which is mid 2019. It can also do cosine similarity search on dense vectors. So whenever we have to build a real world solution, it's always good to build the first cut solution using very well understood techniques. For example, BERT is very well understood. Similarly, Elasticsearch and inverted indices are very well understood. They're heavily optimized, right? So it's always good to do this, but there will also be situations where existing solutions like this may or may not scale. If they do not scale, then you'll have to look at cutting edge research at some of the companies. Again, these are proper hardcore research papers. Like DISC-ANN is a research paper from one of the best machine learning conferences that happens every year, Neuro IPS 2019. It's literally 6 months old research paper, right? So sometimes if the existing cutting edge solutions do not solve your problem, where you have systems which are well tested, well studied, you might have to read cutting edge research and implement them. But this should be the last resort when you're solving a real world problem, because implementing something like DISC-ANN from scratch and making it work will take much, much longer than using a library like Elasticsearch or using a toolkit or a whole platform like Elasticsearch, which has all these inbuilt niceties, and building a solution using it.